this diagram. Looking at the diagram, it looks complicated, but it's simple. We're going to use some theorems here. So you can see we are seeing two circles that intersect at point E and F with a common secant line GF. There is a relationship connecting the tangent line to the two circles, that the two are congruent. So whenever you see two circles that have common secant line, the length of tangents from an external point, they are the same. So this and this are the same. I will prove it later. And since we are seeing tangent lines, so our radius will come to our mind. So we join AH and BI so that we get the radii of the two circles. So we join. So we have the radii of the two circles. And we know that there is a relationship connecting the tangent line and the radius, that the two are perpendicular. So this is angle 90. This is also angle 90. And looking at this, we have angles here and here. So you know this is the radius of this circle. This is also 9√3. So there's a theorem called 30, 60, 90. It's a special triangle that if you have the angle here is 30 degrees, while here is 60, the one opposite 30, if we say is x, the one opposite 60 will be x times the root times √3. So once we know this, we've known this, and also we'll know the hypotenuse, which is 2x, the one opposite 90. So from here, the one opposite 60 is 9√3, the one opposite this 30, the one opposite 90 will be 9. And I told you this length, the two are congruent, so this is also 9. And looking at this is 30 degrees, and the one they gave us is the one opposite 60. So the one opposite 30 will be 3 times √3. Yes, because if you do 3√3 times √3, you get 9. So why the one opposite 90 degrees will now be double, 2 times 3√3, which is 6√3. But they've given us that this is 3√3. From what we calculated, this is also the radius. So therefore, the remaining will also be 3√3. Because if you add 3√3 with 3√3, that's this length and this, we have 6√3, which is 2 times this. So the answer is option A. So what I will do now is to prove that the option is option A. So I'm going to prove how HG and IG, how they are congruent. Okay, from this diagram, you can see that both of these circles have a common secant line CG. So from the theorem that says that CD squared, that CD squared is equal to CF times CG. Length of the tangent, the square of the length of the tangent is equal to external segment CF and secant line CG. So, and that same logic we apply it here, that CE squared is equal to that CF times CG. So what do you have to say? Which implies that this and this are equal. So meaning that CE is equal to CD. This is CD and CE, they are equal, as you can see. So that's